Any questions? Okay, let's look at number 2. Number 2, you're using Hess's law to find the delta H of the reaction given to you. So Hess's law is just a different way to find the delta H of reaction. So instead of using the enthalpies of formation like we did here, we're going to use that series of reactions. Can I erase this bottom? There we go. Okay, so the reaction that we want is this. So we are going to manipulate these 3 equations given to me there so that I can add all 3 of them up to get just this equation. So let's look at the first equation. I need that NO, that's a reactant. I need that NO2, that's a product. But I need them switched, okay? So I need to reverse that equation first off. Then I only need one NO2. This, I only need one of them. That top equation is the only equation that has an NO2 in it. So when I reverse it, I also need to multiply it by 1/2. So let's reverse it and multiply it by 1/2. Right, so for my delta H of that reaction, since I reversed it, I changed the sign, so it becomes a positive 113.1 kilojoules. Then I multiply it by 1/2, because that's what I multiplied the equation by. Okay, so this 1/2 cancels this 2, and it puts a 1/2 in front of my oxygen. Go ahead and do delta H. So the delta H for this reaction is now 56.55. Okay, let's look at the next equation. All right, from this one, we took care of our NO2. We've got 1 NO. We still need 2 more. You look at that second equation, that's the only thing in that equation that we actually need. It's in the products, so we leave that equation just as it is. Okay, so we don't do anything to its delta H. All right, last equation. only thing I need out of that last equation is this N2O. It's a reactant in that third equation, so I'll leave it as it's written. However, I only need one, there are two, so I need to multiply it by 1/2. Right, when I multiply it by 1/2, this 2 cancels, this 2 cancels, and I get a 1/2 in front of my O2. And so I need to multiply my delta H by 1/2.
Why did you change the sign on the first?
I only changed the sign on the first one because I reversed the equation. On the second one, it already had a positive, and I didn't do anything to that one. Okay, now we need to add these three equations up to make sure that everything that we don't need cancels. I don't need this N2 because it's a product. I mean, this is a reactant because it's a reactant here and a product here. Those cancel. Those cancel out. I don't need this O2. Well, I have one of them as a reactant. I have 2/2 as a product, so all of those cancel. Okay, everything else I need, so I bring it on in. I have one NO, I have two NOs, so I end up with 3. Okay, so everything canceled that I needed to, everything stayed that I needed to. Now, to get the delta H, I simply take these 3 numbers and add them together. When I do that, I get positive 157.55 kilojoules. Yes.
So there's something that gets off, just like
Yeah. You manipulate the equation until it does cancel, if you need it to cancel. Mm-hmm.
If you ever find yourself like multiplying by more than like a half on like the top reaction, it's pretty safe to say.
I try not to pick reactions where it's either a whole number or a half. I try. Sometimes I don't look at them close enough, but I honestly hate using a whole half.
Would you ever manipulate like target equation? No.
Never ever change it. Any other questions on test swab? All right. Number 3 and 4. Those should have been fairly easy once you dealt with your temperature unit. All right, number 3 says determine the final temperature of a gold nugget whose mass is 376 grams that starts at, let me write this down. So 376 grams starts at a temperature of 398 Kelvin. It loses 4.85 kilojoules of heat to the snowbank. So if it loses it, it gave it to the snow. So it's negative. And the specific heat of gold is 0.128 joules over gram times degrees Celsius. So units only matter so that they cancel out in your specific heat. So I need this Q to be in joules, this temperature to be in degrees Celsius. To get your temperature in degrees Celsius, you just subtract 273. -20. That's 125 degrees Celsius. Then kilojoules to joules. If I go from kilojoules to joules, you should expect your number to get larger. Because a joule is smaller than a kilojoule. So it's negative 4,850 joules. I moved my decimal 3 places to the right. Okay, now just plug all that into your Q equals MCAD equation. Like okay, so when you get here, you could simply divide both sides by 48.128, right? And that's fine if you do that. However, do not do that when you have to use an equation like this. I think it was the last one on your quiz. Some of you did that and you didn't know how to distribute that negative properly, so it messed your whole answer up. Okay, so when you're doing an equation like this, distribute this term to both of your temperatures instead of simply dividing both sides. You don't know what I'm talking about. Maybe you didn't miss it. And so degrees Celsius equals. Right now, I'm gonna add 125 to both sides. So I got 24.2 degrees Celsius. If you wanted to convert it back to Kelvin, you could have. It didn't tell you what to do, so do what you want. Any questions about number 3? Did y'all get that? Pretty sure that's right. I worked all of these 3 times yesterday, so I kind of remember the final answer for most of them. All right, let's do 4. Or ask us to calculate the internal energy of a system giving off 25 kilojoules of heat. If it's giving off, is it positive or negative? Yes. Okay. And it's changing from 18 liters to 15 in volume at 1 atmosphere of pressure. You could plug in the negative P delta V equation here, but I don't, because y'all usually, if you do, you forget to convert it to joules. So I always come down here and do my work separately. So negative pressure, delta V. My final is 15 liters. Initial was 18. So this is going to give you a negative number. So it's going to cancel out that negative. 15 and 17. 12. So you get positive 4.5 atmosphere time liters. Do not stop there. Now you have to convert that to joules. 1 atmosphere time liter is 101.3 joules. I get 455.85 joules, but really can't stop there either. I need my heat and my work in the same unit. So I either need to convert both of them to joule, both of them to kilojoule. I just converted this to kilojoule. To do that, divide by 1,000 or move your decimal 3 places to the left. So 0.456, what I rounded it to, kilojoules. Now you can go up here and put that in. Add it to your heat, And you've got your delta E. So negative 24.54 kilojoules. Yes. Yeah, so you could have converted this to joules and then added that. Would you like me to give you that number in joules? Be 24,540 joules. You might not have rounded it to 5.4, but that's okay. All right, number 5. Anybody do number 5? You think you got it right? Actually easier than coffee cup calorimetry. That's why I included it here, just to show you. Okay, talks about a bomb calorimeter. Let me remind you of a few. Things. The heat of a reaction is always negative heat of your calorimeter. When you're talking about a bomb calorimeter, we don't use the MCAT equation. This is the only time we ever just use the CAT equation. All right, so it says a 6.5 gram sample of aniline, give you the molar mass, was combusted in a bomb calorimeter. The temperature rose by 32.9 degrees Celsius. Use the information below to determine the heat capacity of the calorimeter. So that's what I want to find, that capital C. So to do that, we're going to use the equation and the delta H of reaction to figure out how much heat is associated with this combustion of aniline. So we're going to start with 6.55 grams of aniline. They were kind enough, I guess I was kind enough, to include the molar mass for you. Just kidding, I got this problem somewhere else. All right, so I've just converted it to moles. Now I look at my equation and I see that for every 4 moles of aniline, I will give off a negative 1.28 times 10 to the 4th kilojoules of heat. All right, so when I solved for that, I got negative 225.1 kilojoules. Okay, so it didn't tell us in the problem what units it wanted our heat capacity in, so we can just leave this in kilojoules. All right, so now I'm gonna go back to this equation right here. I'm gonna plug in heat, but is it gonna be positive or negative? Positive, because that is the heat for the reaction. If I want the heat of the calorimeter, I take the negative, so it becomes positive. We don't know our C. They told us our delta T. It says the temp rose by 32.9 degrees C. All you have to do is divide. So when you solve, you should get 6.84. Any questions there? Probably the easiest problem of all. All right, number 6. Number 6 is like many that you have done. You have to use the density of water. It didn't tell you the density of water, but you should commit to your memory the density of water. Density of water is 1 gram per 1 milliliter. Right, so number 6 says a piece of iron, they give you its mass at 398 K, placed in a styrofoam coffee cup containing 25 milliliters of water at 298 K. Assuming no heat is lost to the cup or surroundings, what is the final temperature of the water? They also give you the specific heat of both substances. So this is the equation I'm looking at. Mass of iron was given to me. 25 grams. So I'm using the MCAT equation here. So there's M, my specific heat of iron. Is that. I'm asked to find the final temperature of the water, but that also means the final temperature of iron. It's the same final temperature. So TF, I don't know. Minus my initial temperature of iron, which is 398 Kelvin, I would go ahead and convert to degrees Celsius. So you say 398 minus 273, you get 125. Okay, that's my iron side. Do not forget to put this negative on the other side. You can put the negative on either side as long as it's there. A lot of you, if you missed number 5 on your, or number 4 on your quiz, it was because you forgot that. All right, now I place the mass of water on that side. I didn't give you the mass of water, I gave you 25 mils of water. If you use the density of water, what's the mass of that? 25 grams. Okay, then you plug in your specific heat of water. I don't know my final temperature. My initial temperature of water was also given to me in Kelvin. So again, say 298 minus 273, you get 25 degrees Celsius. All right, now this is where we start simplifying. All right, this is where I meant earlier where I was saying don't take one of these numbers and divide both sides. Instead, distribute to both temperature terms. 0.225. When you get done, check your answer at 34.7 degrees Celsius, or if you wanted to convert it back to Kelvin, it was 308. All right, there are 6 book problems I want you to do for homework, and you will turn them into me on Thursday. If you don't come to class on Thursday, take a picture of them, email them to me by 9:25 on Thursday, you'll get credit. I do want to see your work just so I know that we're on the same page. But I left the problem numbers in my office, so I'll email them to you as soon as I get to my office. Okay, if you don't have a book yet, make a friend before you leave today. See you guys on Thursday.